Okay, so today we're talking about a very important law in physics. And that is the law of conservation of momentum. That's really messed up. Conservation of momentum. My ink is leaking this morning. Alright, so let's see where this notion of the conservation of momentum comes from, and then we'll see how it plays out in real life. What does Newton's second law say? F equals ma. The net force equals mass times acceleration. And we rewrote it in a second form, which was Ft equals m delta v, right? And this was the impulse momentum form that we talked about, saying that an impulse causes a change in momentum. So that's Newton's second law. What does Newton's third law say?
Every action has an equal and opposite reaction.
Good. For every action, there's an equal and opposite reaction. In other words, there are these action-reaction pairs where if two objects are in contact, or even when they're not in contact, if they're exerting a force on one another, those forces are in equal magnitude and opposite direction. So let's say I have two balls colliding. Ball A is twice as massive as ball B, let's say. As ball A and B collide, which of these is true? The force that A exerts on B is greater than the force that B exerts on A. Or the force that B exerts on A is greater than the force that A exerts on B. Let's vote. Let's say this is red and this is green. Everybody vote. Point to the color. Red is the force that A exerts on B is greater than the force that B exerts on A.
Wait, what is the velocity?
That's math.
JT.
Didn't matter to give us the number.
BA and BB.
Oh, wait.
Oh, okay. Some of you think it's a trick question, and so you want the third option?
Yes.
Okay. So we'll make that third option that the force of A on B is equal to the force on B on A. Is that the third option you want?
Yes.
Okay. So, everybody voting?
I got blue.
Josh, why do you think it might be blue?
Because the third law, opposite equal opposite. So no matter the mass, it's always an equal amount of force. So,
Excellent. If they're hitting each other, by Newton's third law, I know that they have to be exerting equal and opposite forces on each other. So you're right. It is the third option. And it was a trick question. Okay, so please go. Alright. Okay. Well, I'll give you a chance to redeem yourself. Let's go with, here's your three choices again. What about who exerts the force on the other ball the longest? Does A exert a force for a greater time than B? Or does B exert a force for a greater time on A? Or again, for you trick question. Ready? Who exerts the force for the greater time on the other? Right, vote. What's your unconscious, not Josh's conscious?
Josh is better. Right. Vote.
Vote.
Right. You know what? I would say green or something like that.
Come on, here we vote. I want to see you pointing to a color thing where I can see it. All right, I'm seeing a lot of everything this time. He's in green. Tony, why do you think it's red?
Well, I'm just thinking when I would see like the big ball hit a little ball, I would see the little ball go farther. I would think.
Ah, okay.
I didn't work building that, but that's what
because to make the big ball go farther,
it needs more force. So
but they have the same amount of force.
if they both have the same amount of force, then it's going to take. I mean, the same amount of force is going to move the smaller ball more than it's going to move the larger ball.
Okay.
So that's why.
Oh wait, is it time of
See
like
where
it
you're
moving,
coming.
or is it how long they like
How long they
have
How
a
long
force?
how long the force is applied? What do you say, Mason?
I say it has to be equal.
Why?
Because if they're not exerting force, if they're exerting an equal force for an equal amount of time, or not for an equal amount of time, that means one is not in contact for longer than the other.
Right, yeah. How can B be pushing on A longer than A is pushing on B? Right? Because we're talking about a contact force here. And so, in order to exert a contact force, they have to be in contact. So can A push on B for a longer time than B is pushing on A?
Because if they're stopped,
No.
if one stops pushing on the other, then the other stops pushing.
Exactly. If they're not in contact, then neither's pushing on either one. And so, again, it's blue. They're exerting the force on each other for the same amount of time. Okay? And that makes sense the longer I think about it. Because, again, since it's a contact force, anytime they're touching, they're exerting a force on each other. And one can't touch the other without it being touched back, right? That's what's so funny about the game tag, right? Who's tagging? Anyways, anytime you're in contact, both are touching. And so they have to be equal amounts of time. And we said by Newton's third law that they have to be equal in magnitude, the forces. So we have the same force, same magnitude of force occurring on both objects for the same amount of time. Which means what? If it's the same force occurring for the same time, they have to have the same change in momentum. Alright? Now, actually let me back up a little bit. The individual spheres don't have to have the same change of momentum, but the whole system has to have the same change of momentum because the forces and times are the same. Alright? So let's see how that flushes out. Tony's explanation was a very good one because it kept in mind this concept. He sees the smaller ball coming off going faster. So it sounds like there had to be either a greater force or a greater time. And since there was a greater, we knew it wasn't a greater force, it seemed like it needed to be a greater time. The fallacy there was not in that reasoning, it was in what? Yeah, it's not that the velocity is the same. It's needs the momentum, and so he wasn't accounting for the mass. So the smaller mass object, second law, right, requires less of a force to have the same acceleration. Right? Okay, so all that to say that the change in momentum, the total change in momentum before a collision,
So momentum is P.
yeah, remember momentum is P, let's go to mv, has to equal the sum of all the momentums after the collision. And then there's one other little symbol I need. What is it? What is momentum? What kind of quantity? It's a vector. And I know it's a vector because
Direction and
velocity is a vector. Good. And it's mass times velocity. Now, that won't matter as much for us this year because we're going to stay in one dimension in all of our collisions this year. Next year, when we do two-dimensional collisions, it becomes even more.
It's like
No. Yeah. All right? So, what does that mean? If the sum of all the momentums before have to equal the sum of all the momentums after, then that means if I have two balls colliding, right? Again, let's take A colliding with B. Then I know that the momentum of A before the collision plus the momentum of B before the collision has to equal the momentum of A after the collision plus the momentum of B after the collision. Now again, these are vectors, so we have to add them as vectors, but so long as we're in one dimension, the only direction that matters is positive or negative, right? So again, we're going to keep it simple this year. Alright? Now, what does momentum equal? Mass times velocity. So this means that mv for A before the collision plus mv for B before the collision equals mv for A after the collision plus mv for B after the collision. Now I believe on your assignment I'm going to give you in a minute and on the review sheet for the exam next week, I believe I used this form. And this is the form I'm going to have you write on your formula sheet. So M1V1 before, bless you, plus M2V2 before equals M1V1 after plus M2V2 after.